So welcome everybody. I'm Everton de Oliveira from the Groundwater Project, and we're here today to release another very interesting book. It's called Dissolved Organic Carbon in Groundwater System. And the author is Chapelle. Frank Chapelle is a very important researcher from the US Geological Survey, and we'll see why I'm mentioning that. So Chapelle, or Frank Chapelle, during his career with the Geological Survey, he published more than 130 peer-reviewed research papers, 5 books, and received the Meinzer Award in Hydrogeology given by the Geological Society of America. Nice achievement. Welcome, Frank. It's an honor and a pleasure to have you here with us to talk about your new book released by the Groundwater Project. Thank you very much. Could you please introduce yourself and tell a little bit about your career in groundwater, please?
Well, I studied with a very famous geochemist named William Back when I was in graduate school. And that's where I got my interest in groundwater chemistry. And most of my career has been spent looking at the chemistry of water, and specifically the microorganisms that modify the chemistry of groundwater. And the reason that's important from the standpoint of dissolved organic carbon is because carbon is obviously the substrate that bacteria live on. And so my interest in dissolved organic carbon in groundwater basically comes from the fact that microorganisms are one of the processes that really determines the chemical quality of not just groundwater, but pretty much all water. And of course, dissolved organic carbon is one of the important substrates that these bacteria metabolize. Now, one of the things that's interesting about groundwater in terms of dissolved organic carbon, you know, if you look at surface waters, you can see the organic matter in it because there's typically a lot in surface waters. Groundwater is very different. And one of the reasons it is because organic carbon tends to adhere, to zorb onto the surface of mineral grains. And so the concentrations of dissolved organic carbon in groundwater are typically much, much lower than those in surface water. And that's good for potable use of groundwater. But at the same time, it limits the metabolism of bacteria in the ground. So it's the fact that the concentrations are low, and that's typically about 1 milligram per liter in groundwater, is really one of the important indirect water quality indicators that we can look at to understand the chemistry of groundwater. So the other thing that's unusual, or I don't know if it's unusual, but it's characteristic, is that dissolved organic carbon, there are 3 pools or components of organic carbon in groundwater systems. There is the dissolved organic carbon, there is particulate organic carbon, and there is adsorbed organic carbon, where it adsorbs onto the mineral grain surfaces. And the thing is in groundwater systems, typically more than 99% of the organic carbon present is actually present as either adsorbed or particulate organic carbon. Dissolved organic carbon is by far the smallest component of organic carbon in groundwater. So it's reasonable to ask then, well, if that's such a small component of the organic carbon, what is its importance? You know, if it's such a small percentage of what's actually there in available to be metabolized by microorganisms, why is it important? Well, there's really 3 things that make it important. The most important thing is, we mentioned microorganisms. Well, what they're doing is they're carrying out reduction oxidation processes. They're oxidizing iron, for example, high iron groundwater, producing hydrogen sulfide, which is a contaminant that you find. And so because organic carbon is driving those microbial mediated redox processes, that's one reason why it's important. The other reason, another reason why it's important is because the dissolved organic carbon can either facilitate the transport of chemical contaminants on one hand. On the other hand, it can actually retard the transport of dissolved contaminants in groundwater. That's the other thing. And finally, and probably the most important thing about dissolved organic carbon in groundwater is the adsorbed and particulate and dissolved pools of organic carbon interact with each other continuously in groundwater systems. So there's constantly being adsorption, desorption processes. And one of the things is particulate organic carbon is one of the substrates which is a very good adsorber of other organic carbon. So it's constantly being adsorbed. The reason that that's important specifically is because the bioavailability of the organic carbon is really what is important in driving redox processes. Well, how do you measure that? Well, if you try to measure the bioavailability of particulate and adsorbed, it's very difficult. It's a very expensive process, and very few people have done it. Okay, we spent years trying to figure out how to do that. Well, but because of these interactions between the dissolved and adsorbed pools, it turns out that the bioavailability of the adsorbed and particulate pools is mirrored by the bioavailability of the dissolved component. And measuring the bioavailability of dissolved organic carbon is analytically very straightforward, and it can be done by any competent analytical chemistry laboratory. And so because of that interaction, and because of the fact that it's a reflection of the 99% of the other, being able to understand the dynamics of dissolved organic carbon is very important.
Very good, very good. I have a confession to say to you. When I was going to my PhD, and that was more than 30 years ago, I read your book, The Microbiology.
Oh, okay.
I was Jim Barker was my supervisor. I was supposed to work with microbiology. I ended up changing the subject later, but I studied a lot. And your book was one of the first things that I tried. And you had a very interesting the introduction that you mentioned, the difference between a microbiologist and a hydrogeologist. Do you remember that? Can you say that to the others? That was very nice. How hydrogeologists see things, because we get information from separate points and we interpret. And
yeah, I do remember writing that. And I actually can't remember what I said.
No, because for me was interesting because the biologists, they can see the experiment happening and they take
right.
And hydrogeologists, it takes too long, so we get information from here and there, and we make an interpretation of what's happening in between. So the microbiology helps us doing that.
Right. Well, microbiologists, there's induction and there's deduction. Microbiologists in the lab like to perform experiments in a very deductive way so that they can actually see what makes it grow or not grow or whatever else. Well, you can't do that all the time in hydrogeology because the groundwater system is hidden. you can only study it through indirect ways. And so it doesn't really lend itself to a strictly deductive way. It's much more inductive. And I ran into this, it's not so much the case now, okay, but when I first started working on this, there was a real disconnect. If you went to like an American Society of Microbiology meeting, for example, which is the people are talking and thinking in a much different way than if you went to like an American Geophysical Union, or Geological Society of America, because, the geologist is much more inductive. The microbiologists are deductive, and they're very suspicious of the other way of looking at things. And I ran into that a lot early on. It's much less the case now, because when I first started looking at microbiology, this would have been probably 1980, 1981, 82. Groundwater systems were widely considered to be sterile, to not have any life in them at all.
True. That's true. Yep.
And, I was coring some deep sediments, 300, 400 meters deep. We took some of those cores and we started to analyze them for the microbiome, and they popped right out. I mean, you could see them in the microscope, you could grow them in the lab, you could do whatever else. And like I said, that's where my initial interest in dissolved organic carbon came from, was trying to figure out, for a good example about microbiology and groundwater quality is one of the problems that you find in groundwater is high concentrations of iron. And it's fairly common that you get, anywhere from 1 to 5 milligrams per liter of dissolved iron. And when I was in graduate school, and actually when I was doing my dissertation, which was partially on dissolved iron in groundwater, it was considered to be a completely inorganic process. And it turns out that most of those processes, it's interesting when you do your PhD dissertation, you don't want to come to the conclusion that there's something going on here that we don't know about. And that's one of the conclusions that I actually had. And I was lucky because the USGS, the US Geological Survey, hired a microbiologist, and I became good friends with him. And he actually isolated the first microorganism that actually breathes oxidized iron. They're called iron reducers. And I thought, well, let's see if they're in groundwater systems. And so we drilled some core holes. He showed me how to make up the media to grow them. Okay. And there they were. So the high iron that you find in groundwater is a reflection of the microbiology.
Yeah, that's true. Yes, I read something about that exactly, about the iron reduction bacteria. This is it's a big problem for well clogging when
right,
putting oxygen into it. Now it's well known, but at the time it was like it was a abiotic reaction. That would be
right,
hard to explain, right? It's interesting. Very nice.
Well, we had a very famous geochemist. I won't use his name. And and he's much more senior than I was. And I was saying, we get these concentrations of bicarbonate. They are increasing as you go down the flow path. And I said to him, to this very famous geochemist, I said, this has to be a microbial process. And his comment was, now, let's not go off the deep end. And that's a true story. So,
I believe. I believe in you. That's amazing. It's not so long ago. Or are you talking about 50 years or so? About that, right?
Well, I guess it is 50 years now. I kind of don't like to think about that. But.
I sympathize with you on that. Good, good. So back to our dissolved organic carbon. How difficult it is to measure it? How can we measure it in the lab? If someone is willing to measure it, what's the technique he needs to apply? And again, just going on that, what is the difference between humic and fulvic acids and why they appear on the analytical methods?
Well, the fulvic humic dichotomy actually goes back to soil science. What they used to do when they were looking at the fertility of soils, the amount of organic carbon is obviously a part of that fertility. And so what they would do is they would take a strongly basic solution, sodium hydroxide, and they would extract the soil. And so that they would have the organic carbon, dissolved in this. And then what they would do is they would acidify it. And as they acidified it, some of it fell out of solution and was called the humics. And what remained behind was called the fulvics. And that's where that dichotomy came from. In general, the humics are much higher molecular weight than the fulvics, and they have other things. That's less of an issue for groundwater. For one thing, and that's largely because the concentrations of dissolved organic carbon are typically about 1 part per million. And you can't really use that method and make a dichotomy between the fulvic and humic acids. And that kind of brings up another important thing about dissolved organic carbon. We talked about how groundwater systems are hidden, and you can't really directly study them. You can't see it, so you have to use indirect methods. Well, the same thing is true about dissolved organic carbon. Dissolved organic carbon is so complex. There are so many thousands and thousands and thousands of compounds that can make up dissolved organic carbon. Direct chemical analysis, where you actually look at the amount of carbon and oxygen and hydrogen, really doesn't tell you very much about things like the bioavailability or how it interacts with contaminants or anything else. And so you're really left with using very indirect methods. And that's what we do. We use magnetic, nuclear magnetic resonance, things like that. You look at the molecular weight, you look at the isotopic composition, you look at things. All of these things are kind of like a shadow of whatever you're actually trying to study. But in terms of just dissolved organic carbon, you want to know how much dissolved organic carbon is in the water. The technology for doing that is very well developed now. And it basically is an oxidation where you take the water and you do an oxidation event, you measure the CO2 that comes off of it. And that tells you how much total organic carbon is in a sample. That technology, when people first started measuring dissolved organic carbon in groundwater, and that would have been in 1970, there were 2, 3, 4 scientists from the US Geological Survey. And what they came up with was a wet method of wet oxidation. And they would oxidize it, measure the CO2, and that's when it started. And when these people first, the guy's name was Jerry Leinher. What they did was they went to 100 different wells in the United States, and these were fractured granites, these were sands, these were all kind of different lithologies. And they measured the dissolved organic carbon. And what they found was that all of these different aquifers, they all had measurable concentrations of dissolved. Now that would be greater than 0.1 milligrams per liter. There was no correlation between the dissolved organic carbon concentrations in, say, granite aquifers or metamorphic aquifers or limestone aquifers. There was no correlation at all. What they did see was there was a correlation between dissolved organic carbon and the alkalinity of the water, which makes sense because, as we know, the alkalinity, the bicarbonate, is actually produced by bacterial metabolism. And that then is affected by the concentration of dissolved organic carbon.
That's interesting. Have you met these guys?
Jerry Lean here, I did not ever meet him. I came to work for USGS in 1979.
Okay.
And that would have been 10 years after he had done that study.
Okay, yeah. That's quite interesting at the beginning. So he actually correlate it to the microorganisms at all or not?
Oh, no, that was before. That was back when aquifers were still sterile environments.
Yes, interesting. Okay, so what is a regional chromatography model for organic carbon? What is that for someone who doesn't know?
Well, we talked about the adsorbed fraction of organic carbon, okay? Yeah. And so some of the, one of the PhD students at the University of South Carolina, who I was working with, his name is Yuan Shen. And, you know, we were doing a dissolved organic carbon study, and he was doing the analytics, and he was very good at it. And, and because he was an analytic chemist, he thinks like an analytic chemist, okay? And so one of the things is he's saying, well, this aquifer is just acting like a chromatic column that you would put on a, you know, a liquid chromatography kind of thing. And so that got him thinking about it. And so, you know, when we published this study, he actually came up with this, what he called the regional chromatography model, and that's on that's actually on the cover of this book. Now, he was not the first one to think of that. A guy in USGS, a USGS scientist, I guess in 1980, as George Aiken was his name. And he came up with basically the same model because he had noticed that the concentrations, if you looked, he was doing recharge measurements where, you know, water was falling as rainwater. It was dissolving organic carbon. And so the soil had 20 parts per million of dissolved organic carbon. But you got down to the water table and it went down to 5. And then if you went deeper into the system, it went down to 1 part per million. So clearly something was removing this. And so adsorption is one of the things that does it. And so he again said it is acting like a chromatography column. So, you know, it's the two people, they came up with it independently, okay? But that's where this idea of groundwater systems as a chromatographic column comes from.
Yeah, that's interesting. Well, we now it's very common for organic contaminants. We see that, right, because of absorption. We see the same effect, and it's linked.
And like if you work, I'm sorry, if you work on a like say a gasoline spill, okay, so you have a plume of gasoline contaminated groundwater, then what happens is the MTBE goes out in front of everything. The benzene is right behind it, then the toluene, and so it's just separating. But of course, the other thing that's going on is the microorganisms are chewing on it. So
yes. But that's let's, if you assume that, or if we have a contaminant that is not, you know, degradable by microorganisms, but it still sorbs. So then we will have a perfect chromatographic column there, right? Yeah, that's quite interesting. So about the organic carbons, because when we work with contaminants, it's so important. People don't realize how important it is. Even when you go for, you know, remediation, it chews up a lot of your reactant that you're adding to the system, right? That people don't know about that. And it's just
Well, the early research on that is actually interesting because a lot of metal contaminants, arsenic, for example, things like that, they're not very soluble. And yet you still find them in groundwater. Well, one of the things that happens is you have these metal organic ligands. And so the organic carbon can actually facilitate the transport of things like selenium, and I'm not sure about arsenic. But that's actually one of the reasons why people got interested in dissolved organic carbon in the first place, is because of the potential for enhanced metal transport.
Yeah, that's true. Okay, so what are the sources of organic carbon to groundwater? And is there a classification for there?
Well, there's really, unfortunately, I have to use a geologic term here. There is allochthonous and autochthonous. Okay, they're either in place or they're transported in. Okay, dissolved organic carbon can come from the major source for shallow water table systems is organic carbon in the soils above the aquifer. Okay, but at the same time, how does that explain how when you have a deep confined aquifer, where the water is thousands of years old, it still has organic carbon in it? Well, because the organic carbon, the particulate organic carbon that's been originally deposited with the sediments, is continually reacting, and it's adsorbing, and it's doing all these other reactions. So it can either come from the sediments that were buried with the sediments in the first place, or it can be transported in from the soil zone. Those are the two major sources of, the other thing is, it's interesting, if you look at deep confined systems, so you have an aquifer, which is a sand, and it's confined above and below by clay material, okay? When we started looking at the dissolved organic carbon in the aquifers, it's very, very low in these deep systems, usually less than 1 milligram per liter. But then we were taking cores of the clays above and below these aquifers, and we would squeeze the water out and we would analyze that. Well, the organic carbon concentrations were very high. And specifically, they were things like organic acids, acetate, butyrate, things like that. And they were present in concentrations of tens, 20, 30 milligrams per liter. And what was interesting about that is because you have a diffusion gradient between the aquifer and the clay, the dissolved organic carbon was being generated in the clays, diffusing into the aquifer, and that was the source of some of that microbial metabolism that we were talking about.
It's quite interesting, quite interesting. I have a question for you. When we work with the absorption of organic contaminants in subsurface, we usually assume that the absorption occurs exclusively on the organic carbon, which may lead to the thinking that organic carbon is completely hydrophobic. Is it?
It's an important absorbing media, but things like oxidized iron, for example, hematite, things like that, they're very good absorbers of organic carbon as well. So there are, and the other, interestingly, substrate is limestone. It's a very good adsorber of organic carbon. We had a site in Georgia where it was a carbonate terrain, and so there were sinkholes. And we had in the south, we have what we call blackwater streams because the organic carbon is so high, it's 20, 30 milligrams per liter. Well, this river was actually emptying into sinkholes. And so you had a plume of dissolved organic carbon that was going down gradient. and it was gone within 10 miles because the limestone was such a good adsorber. And of course, the other thing is when it absorbs, the microbes start metabolizing it. So it's not just adsorption, it's a combination of the two. So
10 months is quite, well, that's very fast in 10 months.
Well, and again, this was a carbonate aquifer, so the water was moving very rapidly. But that was actually before that. That's probably one of the reasons why I got interested in the dissolved organic carbon in groundwater, was because of that study. Oh, yeah. We didn't know why it was. And you know, scientists, if you don't know, if there's something out there that you don't understand, that's a good thing.
It is.
Because then you write a proposal and get a grant.
Exactly. And it is fun doing it, right? Because then you do learn something. That's very important. That's what science is all about, right?
That's what makes it fun.
Yes, I agree with you. Well, your book finishes with a very significant test that I think. Let me read it here. The chief hydrologic and geochemical significance of dissolved organic carbon may be that it indicates the bioavailability and thus the reducing capacity of total organic carbon present in aquifer systems. That reducing capacity, which determines the kinds of reduction oxidation processes that can occur, is a principal driver for the geochemical processes that determine groundwater quality in both pristine and human impacted aquifer systems. Well, that is quite important. Could you comment on this, please?
Well, that is probably the most significant thing about studying the concentrations and bioavailability of dissolved organic carbon, is because it's not just telling you something about what's in the water, it's telling you how the geochemistry of an aquifer system is actually evolving. And that's by far the most important conclusion that we took from these studies.
Yes, and I can see that. So what do you have an advice for someone who doesn't even care about dissolved organic carbon? What should they do? The hydrogeologists that are watching us here.
Well,
lots of people don't even care about dissolved organic carbon. You know that.
Right. And so John Cherry, who is leading this groundwater project, we had a conversation years ago, and he was working, with contaminants and things like that in groundwater systems. And he says, I always measure concentrations of dissolved organic carbon, because if ever I see a concentration that's greater than 4 milligrams per liter, I automatically begin to suspect some kind of human contamination. And that's actually was published by several people. I don't think John Cherry did it, but he just used that as if you get a concentration of organic carbon that's above about 4 milligrams per liter, that doesn't mean it's contaminated, but it certainly would make you think about it. And so the concentration and the other thing is if you have sources of contamination like agriculture, for example, these things, I remember reading a paper that was published in Australia, and they made sugarcane, and they were growing sugarcane, and of course, all this organic carbon was getting into the groundwater system. And so you had 100 parts per million of organic carbon in the groundwater. So agriculture and cattle feeds, things, and all this other kind of stuff are excellent sources of dissolved organic carbon. And so high concentrations would make you think about some kind of human-induced contamination. Now that's not a hard and fast rule, but it would certainly raise suspicions of human impact on a groundwater system.
Very, for sure. So I would like to thank you very much for this interview and for your nice book. I really enjoy reading it. And again, thank you for your microbiology book as well, because that was quite important in my career. And I have the honor to talk to you right now after so many years. And
well, thank you very much. I appreciate that.
I appreciate that, really. It's from my side. So thank you very much, Frank. It was a very good job. I hope your book is a success because it's a very important topic. People should be aware, and we make a big effort to make it reach hydrogeologists all over the world. Thank you very much. Congratulations for your book. It's very good. Thank you.
Thank you very much.
Thanks. Bye, Frank.
Bye.